Welcome to RISE Learning Machines seminars. I am Olof Nordgren, and RISE is Sweden's public research institute, and Learning Machines is our open weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working on AI to fight climate change. The meeting will be recorded. Let us know if you want to be removed from this recording. And because we are recording the seminars, we also have a great collection of amazing talks on our YouTube channel. So go check that out after you listen to the talk today. And today, I have the pleasure to introduce Nora Gourmelon, who is a PhD student at Friedrich-Alexander-Universität, Erlangen-Nürnberg. Nora is she's specializing in AI for the Earth and working on automating glacier CAlving front segmentation in synthetic Aperture Radar satellite imagery. She's been recognized as an AI newcomer by the German Informatics Society in 2023, and she's working on computer vision, remote sensing, and cryospheric science. The topic today is self-supervised pre-training for glacier CAlving front extraction from synthetic Aperture Radar imagery. And with this said, I will stop the sharing and I will hand over the screen sharing and the word to you, Nora.
All right, thank you very much for the introduction. Okay, then let's start with the sea level. And we all know that it's rising. Actually, if all ice masses on Earth melted, the sea level would roughly rise by around 65 meters. And the goal of this talk is to get even more specific in how much it will actually rise in, for example, 100 years or so. And for calculating the sea level rise, researchers use glacier models because glaciers, of course, store a lot of water, and we need to know how much of the glacier is melting. And one parameter for glacier models is the so-called frontal ablation. Frontal ablation means how much ice is lost at the calving front of a glacier. So the calving front is just the front of the glacier that faces the ocean. And to calculate this frontal ablation, we need to track the calving front position. And we can see this calving front position nicely in satellite images. So on the left side, you can here see a Google Earth image. So it's just an optical satellite image where it's easy to see this calving front here. However, these optical images only work during good light conditions and good weather conditions. So you might know that a lot of these glaciers that end in the ocean are located in the Arctic and the Antarctic. And therefore, there are long periods of darkness. And during these, we would have no data if you only relied on optical images. Therefore, in my work, I focus on SAR images, so synthetic aperture radar images, which send out their own signal and therefore don't rely on sunlight and can also penetrate cloud cover. And with that, we can, in the end, get these, we can track the calving front and how the glacier itself is melting. And we get these nice time series here. But there are a lot of challenges with SAR images that would not necessarily happen with optical images. So first of all, that might be quite obvious. You could already see when you compare to the optical image before. There is a lot of noise in these images, which is actually not noise. It's called speckle. It's rather a pattern because it would be reproducible under the exact same conditions. But it still hinders the interpretability of these images. then glaciers can look quite different in these images. So these 6 images are all images of the same glacier, and actually the calving front has not moved much. So this part here would be the ocean, is the ocean. Then here we have the glacier, and the other parts are rock, snow-covered mountains, and these very dark areas that look like cropped out. These are radar shadows because radar is captured in a side-looking geometry. And then if you have very steep mountains, you cannot look through the mountain, and therefore there's some shadow behind there where we don't have any information available. And you can see that, yeah, this glacier looks a lot different in these 6 images. There are several factors that contribute to that. So, for example, here, the glacier is probably quite dry, and therefore the signal that comes back is stronger. And on the other hand, here, it's probably wet, and therefore a lot of the energy is absorbed. Then here we have some sea ice on top of the ocean, whereas here we have single icebergs with otherwise open ocean. And the most probably challenging image to interpret for us would be this one here, because here we have ice melange, so the mixture of sea ice and icebergs in front of the glacier. And the actual calving front would be here. But as the sea ice has quite similar backscattering properties as the glacier itself, it's super hard to distinguish, not just for AI models, but also for humans, actually. Then another challenge is our sizes. So, of course, we have different glaciers, and different glaciers have differently long calving fronts. So, yeah, the object that we want to see is in reality actually has different sizes, but also the image sizes themselves differ from, not necessarily from image to image, but if we use different satellites, they might have different resolutions, and therefore the same area on Earth has a different image size. And these images are super large, so we need to do patch extraction, and then we lose the global information, just the context information around what we see. So if we would, for example, zoom in on this part here, and just see this and not the surrounding, I myself would not be able to tell if this here is ocean or not. But if I see the bigger picture, I can totally tell, okay, this up here is the ocean, so this part here cannot be the ocean. So this is one very challenging part for AI models. And then lastly, we have a very high class imbalance, because what we want is this single pixel line. And of course, the background has way more pixels, and that it's a line is even more challenging because normal or most of AI models focus on objects and not on boundaries of objects. Okay, so to tackle this task of calving front segmentation, we came up with the benchmark framework, which we call CaFFe. It's short for calving fronts and where to find them. And within the framework, we have a benchmark dataset, which comprises of 5 glaciers in Antarctica, 1 in Alaska, and 1 in Greenland. And the one in Alaska and 1 of the 5 in Antarctica are withheld for testing in the end. In total, we have 559 training images and 122 test images. And here you can see that the dataset spans from 1995 to roughly 2021. And we have data from 6 different satellites. For each of the images in the dataset, we have 2 different types of labels. One shows the CAlving front directly, and the other one is a multi-class segmentation. So with here, the white part is the ocean, the light gray part is the glacier, dark gray are rocks, and black is the radar shadow that I explained earlier. So one idea behind the multi-class segmentation was that we already get a little bit rid of the class imbalance in the model if we do this multi-class segmentation in contrast to directly the binary CAlving front segmentation. The metric that we want to optimize is the so-called mean distance error. That is computed by looking at each pixel of our prediction. So here that would be in red. And we search for the closest pixel in the label, so in the ground truth, and calculate the Euclidean distance to that pixel. We do that for every single pixel in our prediction. And then we do it also vice versa to make it symmetrical and search for every pixel in the ground truth, the closest one in the prediction, and take the Euclidean distance. And with all these distances, we compute the average. And we actually don't give the metric in pixels, but in the end, we compute it in meters. So it's easier to interpret for the geographical later calculations. In the framework, we also have two baselines, one for each type of label. So here we still try to do the direct binary CAlving front segmentation as well. And both of these baselines are based on the unit, but it has an additional Aperture spatial pyramid pooling module in the bottleneck to get those different sizes of the objects. And here are some first results for these, well, not first results, it's the baseline results that we in the end want to compare against. So for the front segmentation model, which was trained on the binary front labels, we get a mean distance of 887 meters. And on top here, there are some good examples where it worked well. So with yellow, we have our prediction, blue is the ground truth, and pink is the overlap of the two. So the model captured at least that there are 3 CAlving fronts in this image, but it didn't get all the details of the CAlving front, and it also confused parts of the coastline with CAlving front. And on the bottom, we have some images where it really didn't work well. So here, for example, it only recognized one of the CAlving fronts, and that very, very poorly. And also it, again, found some, confused some coastline for CAlving front. And in contrast, here are the results for the zone segmentation model. You can already tell by the metric that the predictions were better with only 750 meters of mean distance error. Again, some good results on top and some bad examples at the bottom. You can see that they were better able to at least see that there are CAlving fronts, but they're still not well enough, and so it confuses a lot of sea ice also as part of the glacier. And this one here especially, I think this was one of the ones that I showed you earlier, where we here have ice melange, and it's detected as part of the glacier. Okay, so that's it for the framework, so the benchmark framework that you came up with. And there are a lot of studies already out on CAlving front segmentation in optical images, but also in SAR images, and also studies that do coastline extraction for glaciated regions. And we wanted to see how well or so how far research is in this direction. So we retrained all of these studies on our benchmark dataset and evaluated them. And here you can see the mean distance error for all these studies. So it goes from very high mean distance errors over 5,000 meters to the best one here. And why are some of these so bad, as we would say? That's because were not all designed for SAR imagery. Some were designed for optical images, and a lot of them tested out of in sample, so on glaciers that were already seen during training, just at different time points. So that's why the studies self-reported metrics were better than they are now in the comparison study, because the idea behind them was not to generalize to new glaciers as it is for us, but to work on glacier or images of glaciers that were already seen during training. And we analyzed these results to get to find out in which direction research should focus in the future. So the first thing we looked at was the architecture. So here you can see all that are somehow based on the unit. Then we have the VTG16 as base architecture, DeepLab v3+, a combination of DeepLab v3+ and the VIT, and other VIT-based architectures. And in the end, we could tell that the best basic architecture is the vision transformer. And that's not just because the best performing model is based on vision transformers, but we did some significant tests with grouping these models based on the architecture, and the vision transformers significantly outperformed the other architectures. Then the inclusion of global scale semantic information is very beneficial. So as I showed you earlier, if we zoom in too much, we don't recognize anything anymore. But if we somehow incorporate the global scale or like contextual information, it's easier, or well, at least we get better results for these models that do that. And then it's best to use non-binary labels. So either you train on the multi-class segmentation labels, or you do multitask learning on both labels. And these outperform the models that only train on the CAlving Front binary segmentation labels. Okay, so now let's have a closer look at the best performing model that takes as input two images. One is the target patch that we actually want to segment, and then so-called context patch that is a larger patch around the target patch, which is then downsampled to match the same size as the target patch. And the model itself is based on, as I said, vision transformers. In details like SWIN transformer blocks that are used. And it has two branches. One, the target branch that gets, as the name says, the target patch, and then the context patch. Both, and the context branch, which gets the context patch. Both branches follow a U-shaped architecture, and information from the context branch is fed into the bottleneck of the target branch to enhance the segmentation of the target patch. So to be able to tell more how far research really is here, we also did a multi-annotator study to be able to compare this best performing model to human performance. And you can, by the results, you see that we still have a gap of around 200 meters of a mean distance error. And visually, you can see it here with two samples. On the left side, we have a very good working example. So red are like different shades of red are the predictions of the model different shades of blue, which in this part here are not really visible. That's different annotators. And yellow is the consensus between the annotators. And here on the right side is one where it did not work as well. And as I already told you, these SAR images are also hard to interpret for humans. So here 2 annotators actually did misinterpret this part of like this ice melange as part of the glacier. And one thing that we can tell from looking at the model predictions visually is that the results are super ragged. So it's not as smooth as humans delineate them. So this is one of the downsides of this model. So with the high variability of how glaciers can appear in SAR images and the limited labeled data that we have, these around 600 images of glaciers, we hypothesize that currently self-supervised learning is not sufficient. And therefore, we turned to the hype of foundation models. And the first thing we tried, which is actually already part of this comparison study, but I wanted to go into it anyways a little bit, is the zero-shot performance of SAM, so the segment anything model. So with zero-shot, we don't retrain it anyhow, so we don't fine-tune. We just use it as is, and we feed in prompts. And to generate these prompts, we take our best performing model, the hook former, take its outputs, and for each zone, so for like ocean, glacier, rock outcrop, and no information available, we take the logits and compute the sigmoid over them to get probability maps. Then we threshold those probability maps to only get very high probabilities, and then further erode this high probability maps so that we only get the center part of where the model is sure that it's this specific zone. And then, I forgot to say, SAM is not able to do semantics segmentation. Therefore, we do this binary segmentation, just getting the ocean. So the positive prompt is a random point in the eroded ocean map. And negative prompts are then random points from the eroded maps, probability maps from the other zones. So glacier, rock outcrop, and no information available. And then for prompt feeding, we devised 2 different techniques. One is we call parallel prompt feeding, where we just run this prompt generation that I just explained 5 times and input all of these prompts to the prompt encoder at the same time. And as mask prompt, we use the downsampled ocean logits. And then we run the mask decoder once to get the output. The second technique we call iterative prompt feeding, where we first just generate prompts once, use the downsampled ocean logits as mask, and run the mask decoder. Then we take a valid mask, so the one of the outputs, as new mask prompt and generate new prompts, and then run the mask decoder again. And we do that in total 5 times. So we have the same amount of prompts as in the parallel prompt feeding. For the results here, visually, so this one here, that's the image, and we have the label. And then here, that's the output of our best working model before, so the hook former, where we generate the prompts. So in blue and stars, that's the negative prompts, and green crosses are positive prompts. And on top, we have the iterative prompt feeding, and on the bottom, we have the parallel prompt feeding. And you can see here the segmentation outputs. And from that, after post-processing, the extracted CAlving fronts in blue, in yellow, and in blue, the ground truth again. And you can already visually tell that it's not working so well. And in the comparison study, we can see that here we have the best performing model, which was used to generate the prompts. And then, iterative prompt feeding lands here, and parallel prompt feeding lands here. So it actually worsens the results. So we thought, okay, zero shot doesn't work. So instead, we fine-tune foundation models. And for that, we used 3 different foundation models: DynoV2, PRITV, and SMLFR. DynoV2 and PRITV are, I think, quite well known. They're both based on VAT. And SMLFR is a convolutional neural network-based foundation model. And PRITV and SMLFR are specifically trained on remote sensing imagery versus DynoV2, which is trained on natural imagery. And these are the results we got. So again, those did not outperform our best performing model so far, which was specifically designed for this CAlving front extraction task. And actually, these results here that you see, they were not the first ones that we tried, but that was a complete master thesis that tried to optimize these foundation models in any possible way, trying out different data sets on which they were trained and different model heads and so on. So these are the best runs we had. So we hypothesized that the domain gap between the task and the pre-training data of these foundation models is too large. So we turned to pre-training ourselves. And that means we can again switch to our own architecture. And for that, we first wanted to find an even better architecture than the hook former has. And our new architecture, we call it Tyrion. It's short for Transformer Hybrid with a Residual Convolutional Neural Network. It has a Swin Transformer encoder and a convolutional decoder. Before we said, okay, VAT-based architectures work the best, but they generated quite ragged edges, which we didn't want for our CAlving fronts because we want smooth ones like humans would delineate. And this convolutional decoder directly outputs smooth fronts. So we use CNN here. Then the hook former had a dual branch architecture, which we could eliminate. Therefore, we have less parameters. And we can eliminate it because to get the contextual information, so we don't zoom in too much, we just take bigger patches of the image and then only retain the inner part of the output. So here, the rim of our output, that would be corresponding to this part of the image, we haven't seen enough contextual information. So we wouldn't know what is here. So we cannot be as sure of the output that we would receive for this part of the patch. All right, and then one more information about this architecture. The Swin Transformer encoder uses ImageNet pre-trained weights, as the hook former did as well before. Okay, so back to pre-training. For that, we gathered our own data set of SAR images of glaciers, and we gathered in total 9,562 Sentinel-1 images of 14 glaciers, 13 of those glaciers in Svalbard and 1 in Alaska. And the time period covered is from 2015 to 2022. And with that data set, I tried out several pre-training strategies, which you might know. So I tried out Dyno, SimMim, and SimCLR, but I didn't get any improvements after fine-tuning. And I myself hypothesized that this might be due to the speckle noise that we have in our images. So for example, for SimMim, you need to reconstruct parts of the image, and with the speckle noise, that's kind of hard to reconstruct. So I came up with a new idea, and for each of the images in the dataset, they're not images, but each of the glaciers in the dataset, I also use one optical image. So I found one optical image that shows no clouds and corresponds to the image of to the SAR images of these glaciers. And so that totals into 14 optical images for these nearly 10,000 SAR images. In this dataset, in total, we called SSL for SAR. And with that dataset, I was able to come up with two different pre-training strategies. One we call opt translator, and that is actually very, very easy to understand. It's just that we take our new architecture, Tyrion, we add a single layer convolutional prediction head, and the task is then to translate from SAR image to this one optical image of the glacier. Of course, the CAlving front will have moved in this time, but the static parts like the rock and like the orientation of where the ocean is, where the glacier is, that all stays the same. And that's what the model can leverage like, during pre-training. The second pre-training scheme that I come up with is opt-sim-mim. So that is based on the simple framework of masked image modeling, where we cut the image into patches, mask out some of these patches, and then feed all of them into the architecture. And then from the outputs, we only take the tokens that correspond to the masked patches and feed them into a single layer linear prediction head, which again translates to an optical patch. So here we don't have just this translation from SAR to optical, but we also have this reconstruction task. With those two pre-training strategies, I did several experiments. And for that, we have 3 stages. We have first the pre-trained weights from the ImageNet, so just the encoder that was pre-trained in a supervised manner. Then the 2 pre-training strategies that I came up with myself that use the SSL for SAR dataset. So here we have to choose between the two pre-training strategies. So just one of them is used. And then the third stage is the fine-tuning on the CaFFe benchmark dataset. And here are a lot of visual results. So let's go through them one by one. We have our SAR input image and we have our label. And here we have the result of the best performing model from the comparison study, the hook former, which you can still see. It has quite some ragged edges. Then we have our new architecture with pre-trained weights from ImageNet as the hook former has. And then we have the pre-training with the opt-sim-mim and opt-translator, also both starting from the ImageNet pre-trained weights. And on top, we have all of this without the ImageNet pre-trained weights. So first thing to notice is you should always use the ImageNet pre-trained weights. Without them, it works not good. And then we can see Tyrion itself is already working better than hook former and produces smooth edges. And the pre-training on the in-domain dataset helps the performance even more. So if you look here at the dark gray, so the rock areas, that now corresponds better to the label as only Tyrion, the new architecture. And then one very interesting point is if you compare it's so Tyrion, so ImageNet pre-trained weights to both of the, or either of the pre-trainings on the in-domain dataset with our own pre-training schemes. You can still see that ImageNet pre-training works more, so works better than pre-training only on our in-domain dataset. And that probably has two reasons. One is that ImageNet has 14 million images, and our dataset has only 10,000 images. And ImageNet pre-training is supervised and not self-supervised. But on top of the ImageNet pre-trained weights, pre-training further on in-domain datasets, or at least in this case, in this dataset, helps to improve. So there's still something that can be learned from the in-domain data that was not could not be learned from the ImageNet dataset. Okay, let's go into the quantitative results. On the left, we have the results on the CaFFe benchmark with the hook former with 360 meters mean distance error, and then Tyrion that improves on that, and then both of the pre-training schemes improve on only Tyrion even further. So the difference actually is bigger with the pre-training than just the new architecture. But we didn't stop at benchmarking. We wanted to see how it works in a kind of real-world scenario. So as our geography collaboration partners actually use it in the end. And for that, first of all, we had to do some additional post-processing to be able to compare to the multi-annotated study. So there were some post-processings that had to be done for the humans. So as it was done for the humans, we also do it for our models. And then we did ensembling and test time augmentations to get even better results. And with that, our best model here, it's pre-trained, has a mean distance error of 75 meters, which is very close to the human performance of 38 meters. You can also see that in this diagram, how we could improve upon the best performing model from the comparison study to here Tyrion, then pre-training on Tyrion, and then an ensemble of Tyrion and ensemble of the pre-trained models that in the end gets quite close to the human performance, but we still have a gap of around 30 or 40 meters here. So there's still something to improve. Here are some visual results where you can compare the different annotators to our ensemble prediction. In yellow, we have our ensemble prediction, and the different shades of blue are the different annotators, and pink is an overlap between the prediction and one of the annotators or several of the annotators. And at least in this image here, you can already see that the prediction kind of looks like just another annotator. And one advantage of ensembling is that we can also generate uncertainty maps. So for the same example that we had before, we can generate for each of the classes one uncertainty map that shows in this example here at least that this part of the glacier, the model is rather uncertain whether it is glacier or ocean, but on like the uncertainty maps for the no information available area, they show us that it's mostly super certain where the NA areas are. And for rocks, it's more on the boundaries between the other zone to the other zones where it's uncertain. All right, so let's conclude. We have a new hybrid one-branch architecture, which allows us to integrate contextual information very naturally. So we just input a large patch and take the inner part of the output. And due to it being hybrid, we also get smooth front delineations. Then we were able to enhance the performance of a model that only gets SAR images by using multimodal pre-training with also optical images. And this pre-training strategy, or both of them, are quite data efficient, at least optical data efficient, because we don't need matched SAR optical image pairs, but just one optical image from each glacier. And then we can tell that in-domain pre-training is beneficial additional to ImageNet pre-trained weights. So it still enhances the performance if you have some in-domain data that you can pre-train on. And lastly, our ensembles achieve near human performance and also allow us to get uncertainty estimations, which the geography collaboration partners can use to also get uncertainty estimates for their parameters. So for the frontal ablation that they calculate based on our results in the end when they use our models. And this frontal ablation can then be used to hopefully enhance glacier models and therefore the estimates of sea level rise. And as I said, there's still something to be done. We are not at human performance, we're just close to it. So a colleague of mine is actually integrating time series information into our models. So he uses time series as input, not just single images. And our collaboration partners are currently applying the models in Svalbard, but they will also in the next year or so apply it throughout the Arctic to get estimates of frontal ablation in the entire Arctic. Well, with that, I can only still thank my lab, so the pattern recognition lab at the FAU, and the MOCA International Doctor Program, which is led by the Geography Department. And without all of these awesome people, I would not be able to do my research as is it now. And with that, thank you very much for your attention, and I hope you have a lot of questions.
Thank you, Nora. Exciting stuff.
Thank
you
you.
get virtual applause here. I'll start off with a question. So your pre-training works with the one with the optical images. You say you only use one image, and that means that you don't really know if the alignment of the front is close or not to the SAR images. Have you looked at having aligned images? I mean, as the downstream task is actually looking at the very front, perhaps such alignment could also help improve the downstream task.
It could certainly. There are already pre-training schemes for aligned image pairs, but it's not always possible to get these image pairs because, as I said in the beginning, the optical images are only available during the summer months. And we want to use all the SAR data that we can obtain for pre-training. So it has seen a bigger variety of how these SAR images can look. And therefore we thought, okay, let's stay with the data efficient optical approach. So we had less data curation and we were faster able to use this pre-training. But yeah, certainly, if we would have aligned image pairs for all of our SAR images, that would be ideal, but we don't.
Okay, thank you. Other questions?
I've got one following on the kind of data setup and access. So, I mean, we kind of know that all of these models, and especially the self-supervised, do very well when you have huge collections of data. you mentioned sort of 9,000 or so for the self-supervised setup, and I guess was it like 5 to 7 different actual glacier sites? Like, how do you think the performance of these models would scale if you managed to magically increase that by like factor of 10 or so? And how much access to this data will you get in the future? Like, is it getting easier?
Yeah, so in our benchmark data set that was labeled, we had 7 glaciers, and it's 14 glaciers in this unlabeled data set.
Mm,
That's not much, you're right. We actually, I can tell you, we got some more labeled images now
mm,
from the entire Svalbard, because we thought, okay, we don't actually need to generalize to unseen glaciers if we have a label for every glacier that in the end we want to
yeah.
do inference on. So we used that, we further trained our model, actually the time series model that my colleague built now. And that enhances the images again. But I have to say, I'm not sure in the end. Well, actually, I am. On the benchmark, it did not improve much on the
Mm,
evaluations, but it improved a lot for our inference in Svalbard. So we have some new testing images there, and they're training on more varieties, or maybe because it trained on the seen glaciers, like on the same
yeah.
glaciers. Yeah, that helped.
Mhm.
And for availability, it's actually good, I think, as far as I know. So we are using Terabyte, that's run by the DLR, the German, what's it called? Yeah, I don't know the English term for it, but
Yeah.
it's kind of the NASA of Germany.
Yeah.
There we have it's a new HPC cluster, and you can get the pre-processed images from them. But it still takes a lot of time to get those pre-processed. So I think we waited for some months always to get new images. But I
Mm.
think that's because it's quite new, the terabyte, and it will be faster in the future, I assume.
Okay. Good, good. Thank you.
You're welcome. Thomas, I think we can't hear you. At least I can't.
Okay, now better.
Yes. Okay.
Yeah, I was wondering about ensembles here. I didn't understand what you ensembled. What are the different models that you
Oh, so it's just retrainings of the same model. So because it's a stochastic process, if we retrain, it will result in new weights, and we use like 5 retrained versions of our own model, and do an ensemble of those.
So it's just the starting weights, so the starting random weights that are
Yeah,
different between these models.
exactly.
Okay, thanks.
You're welcome.
Interesting.
Do we have one final question for Nora?
I have another one in case no one else.
Yeah, go ahead.
So I was wondering just a bit on the error metric that you're using. So what if you have a model that either outputs no prediction at all, or there's several different fronts and it sort of covers one? Do you, for all the other fronts, effectively compute the distances to that existing data, or if there's nothing at all, is there a standard distance that gets sort of added?
Okay, so we don't output any CAlving front. We actually have a different metric that is just the count of images where we have no front predicted.
Hmm.
I didn't show it because the really good working models have CAlving fronts for every single image, even if they're bad in the end. And otherwise, if we have just one CAlving front that's recognized, this metric is not perfect. It gets the Euclidean distance to the closest CAlving front in the
Hmm.
label.
So they're all kind of counted as one long
Yes.
thing, which is interrupted and then it's sort of duplicated. Okay, cool.
What is an acceptable error rate for your geography collaborators?
Great question. Actually, they just tell it to me qualitatively, so they don't themselves have a number in mean distance error. They just tell me, okay, it looks shit or it looks good, we can use it. But yeah, I mean, we're actually already quite good, like with this near human performance. It's just if we can, like, with some images, it doesn't work. And what we do now is that we, during post-processing, just try to filter them out where it's not good enough. And then this near human performance might actually already be human performance, so that is sufficient.
Cool. So if there are no more questions, then we'll round up this seminar, and I will say welcome back in 1 week, 7 days, November 20th. We'll have the next seminar, which is with Katarzyna Michalowska from SINTEF in Norway. She's going to talk about multi-resolution learning with neural operators and long short-term memory neural networks. So welcome back then. And thank you so much for today, Nora.
You're welcome. It was my pleasure.